So we're going to start on vibrations and waves, and that will lead us into sound, and we'll end the year with sound. No, yes, vibrations and waves, and then sound. A loud, loud.
Yeah.
Imagine a mass spring moving back and forth on the spring shown. At which position, A, B, or C, are each of the following quantities the greatest or the least? So which one has the greatest force? Right, so the spring is pushing out on it. And at C is the farthest and it's pulling back on it. See? Which one has the greatest velocity? Well, it's like it go back from A, B, C, B, A, B, C, B, A.
Because it's going the fastest.
Okay.
You're asking the velocity.
Yeah.
Yeah, but C's slowing down because it's got to go back.
So then acceleration, which one has the greatest acceleration? A and C? Well, we'll find out. Kinetic energy. You guys agree B? C? Potential energy.
C.
Potential energy would be C. Because it's stopped.
Well, it's A. A is stopped.
No. It looks like it's just springing forward.
Well, it's not.
Yeah, you do. It goes A, B, C, B, A, B, C, B. It's like,
Press right there. That's as much as that spring can press.
It's like more
Tyler, I think I would know.
harder.
I can't even see it. It's
and then mechanical energy.
So it's
C. It's C.
A minus.
Okay, let's look at springs first. Hooke's law. Hooke's law is equal to as the elastic force. So the force of the spring is equal to negative K, and K is a spring constant. So each spring has its own constant, and it won't change for that spring. Times X is the displacement. For each spring, it will be different. But for this, if you're dealing with the same spring, it always stays the same.
Spring force, which is
F elastic.
elastic, equals
Negative, and then like parentheses K times X.
so that's
Yes. For that spring. So the minus sign is needed because the force and displacement are in opposite directions. So if I have a spring, let me go find a spring.
So your spring force is always negative. Jaka, I'm getting tired of you.
Thought I had springs in here. Maybe it's in this cup. Look what I found. I've been looking all over for burn spray. It's my burn spray.
This one gets burned.
Yes.
Well, that would be bad if you didn't know what it was. They could just take a safety shower. I watched that.
I don't think I noticed it.
I watched it.
I only see my really big springs. Hold on. Oh, here we go. Okay, so here's a spring. This should be enough.
Look at that, we're almost done with notes.
Oh, yeah.
Wow.
We just flew through that. You have to go.
Oh, jeez.
Oops.
Visual concept, yeah.
Okay, so let's look at the spring. The minus sign is needed because the force and displacement are opposite directions. So it's saying in equilibrium, this would be equilibrium, the normal force. So when you stretch the spring any farther, the displacement would be from here to there. That's the displacement. So if I displace it downward, if I'm pulling downward, which direction would be the force of the spring?
Upward.
It's pulling upward. So that's why there's a negative sign, because it's the opposite. So this would be the,
Displacement.
so this would, when we were doing A, would be up here. This is, C was right here, or B was right here, and C would be down here in that picture. High up there and down here, right? Because there's potential energy to pull it up. Not necessarily, because it starts oscillating at the same rate, depending on if your displacement was the same. So the displacement would be from here, letting it just hang right there. Stay here. And then from right here, this point, measuring from here to where, however far down you
So you
pull.
just go like from that minus.
This, yeah, this would be displacement. Yes. Okay. This spring has its own spring constant.
Are you kidding me? He's wearing a sweater vest. Of course he won.
Alright. What are we learning about? Waves.
Right now we're talking about waves, or the springs in Hooke's law. K measures the strength of the spring, so if you have a larger K, it's a stiffer spring versus a low K would be a very loose spring. Let's see what this says. You guys are going to have to listen really close because I don't have it plugged in. But you'll be able to hear it from my computer. Just got to listen.
The spring constant determines how much force a spring will exert for a given compression or expansion. For example, if we attach 1 kilogram weights to each of these springs, we see that they stretch different amounts. The larger the spring constant, the stiffer the spring, and the more force that is required to stretch it. The spring constant depends on the type and amount of material a spring is made of and how the spring is formed.
Okay. Yes, there is a spring in your pen.
Hey. Hit him.
Did that hurt you more than it hurt me? I think so.
What did you try to do?
I felt the thud. That was about it.
Okay, a slingshot consists of 2 rubber bands that approximate a spring, so they act like a spring. The equivalent spring constant for the 2 rubber bands combined is 1.25 times 10 to the third Newton per meter. How much force is exerted on a ball bearing in the leather cup if the rubber bands are stretched a distance of 2.5 centimeters?
Well, we have the distance.
Yes.
Myers, you look really smart for that, right there. Like,
Negative K, so K is 1.25 times 10 to the third
So
Newton
what's K again?
spring constant.
Spring constant. Times 2.5. That's your displacement.
Ah, but we need it in meters. Look, this is in meters.
So it would just be 0.025. Yeah.
So what do you get? 31.25 Newton. Okay, so what is this negative telling us? It's just in the opposite direction. So if you're pulling it back, then the force is forward. like a slingshot. Think about it. A slingshot you usually pull backwards. So the force, the displacement is backwards. The force is forwards. They're opposite. Just like what we said, right? If we said, if we pull this down, the force is going to bring it which way? Up, right? It's opposite direction. It's trying to come back to equilibrium. So the force is always changing. Like in this, the force is up here, but down up here, where's the force? Be down, up, down, up, down. So the force is always changing. No. Right, well, if we put the negative sign in, that's because it's going the opposite direction. So, right, it is going the opposite direction. So since the displacement is positive, then the force would be negative. See what they have. There we go. It's just in the opposite direction. That's all that negative is telling us. So if you put the distance as negative 0.025, and you can, then the force would be positive, because it's just opposite. I would put either opposite the displacement, or in this case it would be forward because you're pulling it back. Simple harmonic motion results from systems that obey Hooke's law. So anything that obeys Hooke's law and oscillates, goes back and forth, then it's called simple harmonic motion. SHM is a back and forth motion that obeys certain rules for velocity and acceleration. Okay, so here is our block on the spring that we had in those pre-lab question. So here so this line right here is equilibrium. Like if I didn't have it pulled and it's not displaced. So our displacement is here, x. Our elastic force is in the opposite direction. Right here, x is 0. So there is no force because it is at equilibrium. Here, the x is negative, and the force would be positive in the opposite direction. So where is the force a maximum? A and C, yes. Where's the force 0? Where's the acceleration a maximum? A and C, because it's slowing down. Right here, the speed is 0, the acceleration is 0. Okay, so it's, or not, speed is not 0. The speed is at its greatest. And then it's slowing down on each way. So it's accelerating, decelerating. So A and C, yeah, the acceleration would be C. The acceleration is 0 here. But the velocity, the maximum would be B. And the minimum would be, or 0, I guess, velocity 0 at A and C, because it's actually a stop its motion to go change directions. This is all called simple harmonic motion. Another one.
When an object vibrates or oscillates at a single frequency around an equilibrium point, it is moving in simple harmonic motion. Pendulums with small equilibrium point, it is moving in simple harmonic motion. Pendulums with small amplitudes and springs that are not stretched too far often move in simple harmonic motion. The velocity of an object in harmonic motion is 0 at the outer points of its oscillation, where the force on the object reaches its maximum. The object has maximum velocity at the equilibrium point, where the force is 0.
Okay. So what are the two objects they said behave in simple harmonic motion? No? What she said, the two objects that behave as in simple harmonic motion. And what is, it isn't stretched too far, and the pendulum has to be what? Small angle. So you can't hold it way up here and keep going. Small angles. That's what we'll do with the lab on Wednesday. Simple harmonic. Okay. Shh.
An object that oscillates about a point of equilibrium exhibits harmonic motion. The simplest form of harmonic motion is called simple harmonic motion. In simple harmonic motion, position versus time can be plotted by a sine curve. The force exhibited in simple harmonic motion is described by Hooke's law. The restoring force equals negative k times x, where k is the spring constant and x is the displacement of the object. Since the force is doing work on the block's kinetic energy changes with time. Similarly, the elastic potential energy changes with time. However, the total energy of the system is constant. When the block is at its left extreme, the
This is
kinetic
part of
energy
the
is
questions
zero,
they asked at
but
the beginning,
elastic
right?
potential energy is at a maximum. The same is true at the right extreme. At the midpoint, the potential energy is zero because the spring is relaxed. However, the kinetic energy is at a maximum. Because of this, the total energy does not change.
Okay, so this is when it's right here. The block is right here. This is the energy. So right at this point, we'd have high potential energy, no kinetic energy because it's not moving. Right in the middle, at the equilibrium point, we have all kinetic and no potential, and then out in this direction, we have all potential and no kinetic. No. Pendulums, same idea. When you pull the pendulum out, there's a restoring force to come back to equilibrium, which is straight down. Part of that is because of gravity. So at small angles, it's proportional to the displacement. So it's considered simple harmonic motion. Right, the force of gravity just has a different effect on it. We use small angles.
Oh, got the answer.
So you're going to have to use simple, or not, the triangles, yep, where we have the gravity force on a lot of times they'll call this mass on here the bob. And so the bob on the pendulum, it would go straight down. And then you're going to want to find whatever angle this is the same as this angle right here. And then you would have FGY and then FGX. So the restoring force would be the FGX part. Right here. So yeah, this theta is equal to this theta. So, okay, let's look at this. So you would want to use tangent, cosine, sine, which one? We want to find this right here. I need to use something other than yellow. Okay, here's our right angle, right? So here's the FGX also. And FGX is equal to our restoring force. So, what trig function would we use? We know FG is 10 newtons. We know the hypotenuse. We're looking for FGX, and we know the. So sine theta. So the first one, let's just do the first one. It's 3 is equal to what?
Oh, up there.
The angle's right here. FGX over FG, which I guess we know FG is 10, so let's put that in there. So when you calculate it, you should get 0.523. Someone do that. Make sure it's right.
I technically read an article.
Okay.
I read an article that said, you know that Hubble telescope
Mm-hmm.
saw a black speck that when zoomed in had like millions of clusters of stars, and one was so big it defied the laws of physics because physics said something couldn't be that big or something like that. So we're being taught.
So everything being taught is a lie.
Yep, that's all a lie.
Because it defies it. If it's really that big, it's false. But
Maybe we just gotta alter our theories now. Oh, are the forces proportional to displacement? Only for small angles. Okay. Simple pendulums. Let's see what they have to say about pendulums.
A simple pendulum consists of a mass called the bob
Mass called a bob.
hanging from a string. The restoring force in a
No,
simple
Jacob,
pendulum
stay.
is due to the force of gravity. If the bob is moved slightly to one side, we can examine that restoring force using a free body diagram. Tension acts on the bob through the string. The force of gravity can be broken into two components. One component exactly opposes the tension. The other is perpendicular to that.
This is
This
y
component
x.
is the restoring force. When the displacement of the pendulum is very small, its motion approximates a straight line. In addition, for small angles, the restoring force is proportional to the displacement, and the motion of the pendulum is simple harmonic motion.
Okay. Okay, so what do you think now that we've gone through this all? Where's the force the greatest?
A, right?
A and C. And where is it the least? Where is the velocity of the block greatest? And where is it the least? Acceleration is the greatest.
E, right? No, A and C.
And the least?
So A and C are pretty much the exact same except location.
Yep, they're just opposite, but they're the same greater maximum.
Gotcha.
Kinetic energy is the greatest
B.
and least because it's not moving at A and C. Potential energy is the greatest at and least B. And last one, mechanical energy is, yeah. So when you add kinetic plus potential, so if kinetic's high, potential's very low, so it evens out. But if, what did I say first? If potential's high and kinetic's low, then it equals out.
So mechanical is always the same.
Mm-hmm.
No matter what.
Yep. Yep. Because kinetic and potential just transfer between each other. Okay. Let me go get the worksheet.